Throughout this course, we have examined the world of data centers step by step. We began by understanding what they are, how they are classified, and how their energy footprint has grown. We then explored their components and identified where energy is consumed, before moving to strategies for improving efficiency, covering IT optimization, cooling systems, and sustainable infrastructure design. Finally, we saw how digital tools, automation, and artificial intelligence can transform operation, enabling smarter monitoring, predictive maintenance, and real-time optimization. In this concluding session, we'll look ahead to how data center electricity demand could evolve in the coming decade, considering different scenarios and the challenges that may arise if the growth is not carefully managed. Data center electricity consumption keeps rising rapidly, driven by two main forces: the explosive adoption of artificial intelligence and the continued digitalization. The global server stock is expected to grow by more than 60% by 2030, partly due to the extension of server lifetimes. Accelerator servers grow even faster to meet the demands of AI workloads, though they still represent less than 10% of the total server fleet. Cooling systems become somewhat more efficient thanks to advances in the airflow management, liquid cooling adoption, and smart operational practices. As a result, global data center electricity demand will nearly double by 2030, reaching around 945 terawatt-hours, just under 3% of global electricity consumption. According to International Energy Agency, this is the base case scenarios of data center electricity demand. However, alternative scenarios have been considered that paint very different pictures. The lift-off case imagines a world where AI adoption and demand for digital services accelerate even more strongly. In this scenario, global data center demand surpasses 1,700 terawatt-hours by 2035, representing over 4% of the global electricity consumption, and putting significant strain on power systems unless careful management. On the other hand of the spectrum, the high-efficiency case assumes the same demand for digital services, but pairs it with aggressive efficiency strategies. More enterprise data centers are consolidated into highly efficient hyperscales or colocation facilities. Finally, the headwind case explores a slower growth pathway, in which digitalization advances at a reduced pace, AI monetization faces barriers, and local grid constraints delay data center construction. Installed IT capacity grows more slowly and eventually plateaus, resulting in far lower electricity demand growth than in the base case. Whichever scenario plays out, the rapid growth leads to several risks and challenges that must be carefully considered. To face these problems, the sector is testing new solutions. Many operators are expanding the use of renewable energy through solar, wind, and hydropower. Some are experimenting with advanced options like small modular nuclear reactors, large battery systems, or heat recovery that reuses waste heat to warm nearby homes and buildings. These approaches show that the energy efficiency is not just about reducing consumption, but also about rethinking how resources are used. As data centers grow, so do their fundamental power requirements, not only in terms of average consumption, but especially in terms of peaks. Intensive use of servers can cause sudden consumption spikes that the grid is not prepared to handle. Moreover, in some regions, data centers already consume about 10–25% of the local electricity supply, leaving little margin for other loads. This can lead to network congestion, higher prices for energy use, and the need for significant investment in new generation and transmission of capacity. One potential solution to this problem is the increase in penetration of renewable energy sources. As wind and solar power become the backbone of many power systems, data centers must align their consumption with variable generation patterns to avoid relying too heavily on fossil fuels. This means shifting flexible workloads to hours of high renewable output, using on-site storage to smooth peaks. Another challenge is technological change. Data centers built for traditional cloud services may not be suitable for high-density AI workloads. Hardware and cooling needs are evolving so quickly that facilities risk becoming outdated before recovering their costs. In addition to this, there are operational risks, including vulnerabilities to extreme weather events, such as heat waves and storms, and cyber attacks that could disrupt operations. Finally, social and environmental considerations must be taken into account. Data centers may compete with local communities for electricity and water, particularly in regions where these resources are limited. If projects are perceived as unsustainable, public opposition may grow, leading to stricter siting regulations. Operators are increasingly expected to be transparent about their environmental impact, including their carbon emissions and water usage, and to have a positive impact on the communities in which they operate. Despite these risks, the future holds many opportunities. Hardware is becoming more efficient at all times, and AI itself is becoming a key tool for optimization. Smart algorithms can balance workload, reduce cooling demand, and identify issues earlier than the human operators can do. Meanwhile, new metrics such as carbon and water usage effectiveness help the industry to measure not only energy efficiency but also environmental impact. As we close this course, one key idea remains. Data centers are critical for our digital world, but they must grow in a sustainable way. This sector must keep innovating through more efficient hardware, smarter software, renewable integration, and advanced planning tools such as simulation and digital twins to manage demand responsibly. Policymakers and industry leaders must collaborate to ensure that data centers expansion is accompanied by investment in clean energy, resilient infrastructure, and equitable access to resources. By doing so, the promise of a more connected, data-driven world can be realized without creating unacceptable pressure on the environment or society.